Thank you for this presentation. Hello everyone. My name is Meriem Chaaben, and I am a PhD student at Université de Montréal as a member in Geod's group. And I am interested in AI for MD in general, and more specifically in using AI techniques to assist modelers during their tasks. Today, I will be presenting an interesting approach where we leverage few-shot prompt learning to do model assistance. And we incorporate that in a tool, we call it Maple, referring to Model Assistance Prompt Learning. I just want to mention that this research work involves a collaboration with Professor Lola Boguino from University of Malaga, Professor David Istvan from McMaster University, and of course, my supervisor, Huari Sahrawi. Okay, so let's start. So all of you are familiar with model-driven engineering concepts, and you know that this systematic approach for describing and designing complex systems is very important at the design phase, independently from any development process to kicking off a project. We also know that domain modeling itself is a complex task because it needs at the same time good knowledge about the domain itself and about the modeling formalism. This is why we are talking about model completion or model assistance. The goal is first to obtain a complete and compact model, to then gain time and do the task faster, and finally to minimize the cognitive effort path. So let's say we have a model under construction. We take class diagram as an example, and everyone can tell in this case that elements or concepts are missing. To complete this, we could use suggestions resulting from classical AI and natural language processing techniques. We could complete with more classes and association, as you can tell intuitively. However, all these approaches require data, but domain modeling data is scarce. Besides machine learning, models should be trained from scratch, which is time-consuming and requires a lot of resources. And finally, we definitely cannot train a model for each specific modeling formalism. So our idea is then to leverage general concepts already encoded in the powerful left-to-right large language models. We actually want to benefit from these large language models that are trained with many general concepts, but this does not map directly to our modeling formalism, which is in our case class diagram. So in our work, we suggest building the semantic mapping between what these LLM learned and the formalism in which people want to model their work. So we start by providing the LLM a description on how to reply to our queries, which is here generate related concepts. I add two relevant labeled samples, or what is called shots. Here we have the domain model for hospital system and reservation system as shots. Concepts that are associated together to each other, we introduce them as group. Then we encode our model under construction, which is the banking system, the same way we did for the other examples or shots. We query the engine, and in this example, we have GPT-3 as LLM, and as a result, we obtain a text. So another semantic mapping is used to extract the useful elements that could be incorporated into the initial model, as you can see. Within the same formalism, which is in our class diagram, we could have semantic mapping in different types. For example, like besides suggesting class names, we could suggest attributes. We introduce a different prompt, a different task description, like here, generate missing attributes, and a number of shots manufactured through an appropriate semantic mapping. And we follow the same process. Also, we can have this for any other formalism, like dynamic domain modeling formalism, as an example here, activity diagrams, which means that this approach could be generalizable. The main work is done at the level of semantic mapping, as there are strong precedence and sequence constraints to consider in this formalism. We defined simple transformation rules to match the elements of the activity diagram to the appropriate keywords that conform the prompt that we sent to GPT-3 here as an example. And we follow the same process, another semantic mapping, and incorporate the obtained result to our model under construction. So to evaluate the approach, we focus on two evaluation axes. The correctness of recommended elements to complete domain model and the usefulness of suggesting modeling elements on modeling tasks using this new paradigm. So, for the first axis, we have evaluated the idea on domain models represented as class diagrams from a public repository. We set the adequate hyperparameters for each task, and we automated the reconstruction process and simulated the behavior of a designer by either accepting or rejecting suggestions based on whether they appear in ground truth, which can be regarded as a worst-case scenario. We obtained promising results if we compare them to previous work, for example, recall average of 0.7 for attribute names. For the second evaluation part, which focuses on the usefulness of this approach and the impact of leveraging LLMs to do model assistance, we take advantage of a tool we built that is named Mabel after Model Assistance Prompt Learning. It is built within the robust and flexible environment Eclipse, more specifically the Eclipse modeling framework. I think you are all familiar with it, EMF, that provides the tools and capabilities to define the data structure of Mabel. We employed, on the other hand, the Sirius plugin to construct our DSL-based graphical editor. So Sirius operating as a language workbench within the Eclipse platform and is tailored for graphical modeling languages. It leverages the data models created by EMF to produce visual representation, which are key for user interaction with the models. Then, an integral part of Maple is the recommendation module, leveraging the power of, in our case, GPT-3, one of the most advanced LLMs. And of course, we employed the appropriate Java code for making API calls to OpenAI and request the engine. Maple's design includes three distinct recommendations modes, which we will be presenting now to understand better the features provided. So we start by the on request mode. Here, users can actively request specific predictions at any point in the modeling process, allowing for targeted searches for attributes, concepts, or associations. As you can see, it is possible to ask for missing concepts or class names. And we will have a list of potential class names. The user can choose from it or just reject it. Here we are looking for classes, and we could also do the same for attributes or associations and add as much as we want to the canvas. And of course, it is possible to add anything else from the palette provided in the tool. The list of associations could be added. The second mode, which is automatic mode, where the system automatically suggests relevant concepts and operations as the user adds element to the model under construction. So we have the list of classes and another one for associations in the left. And when accepting any one of these concepts to the canvas, a list like this list is updated, and the user will be able to choose from it. Also, a list of attributes will be provided if one class is added to the canvas. Finally, we have the at-end mode. Users here can request a comprehensive set of suggestions for potential enhancement after completing their model. And with just one click, they will be enabled a final review and refinement of their work. So different lists will be provided to choose from to add to the canvas, one for classes, one for attributes, and the final one for missing associations. This is for potential attributes. And as I said, at the end, a list of associations could be from which we could add to the canvas. So we use the tool the tool mainly for our second evaluation process, which represent what we are currently doing. We thought about doing a user study, so we focus on collecting two types of data, quantitative data or qualitative one. So an example, like a list of metrics that we focused on for our quantitative analysis was time to complete a task, diversity of solution, and we also try to assess the contribution of these suggestions. And as for qualitative analysis, we provided questionnaires for participants to answer, and we collected different metrics for that. So to conclude, for our research work, we were able to prove that the LLM-based approach is promising when it comes to model completion, and modeling assistance, which made us to integrate it to a modeling platform using Eclipse and Cirrus more specifically. We strongly believe that we need to focus on evaluating the usefulness of that and see its impact on integrating it and doing the recommendations to during modeling tasks. As key takeaways, we assume that LLMs are offering a paradigm shift in the way we are building things, and more precisely in building models. Besides providing only few shots to the powerful large language models is enough to complete a complex task. The effort here is to elaborate the right semantic mapping. And finally, this approach is very easy to generalize with different formalisms. We not only tested that with static diagrams, class diagrams, but also we evaluated it on dynamic diagrams such as activity diagrams. Thank you.